So let's say we want to know the black body, we'll call it BB emissive power, in the range from 0 to, say, lambda 1, where lambda 1 is some arbitrary wavelength. So if we did that, I guess we'd have to take this integral. So we'd write it as follows: EB from 0 to lambda 1 is equal to the integral from 0 to lambda 1 of Planck's law C1 over lambda to the 5th exponential C2 over lambda t minus 1 d lambda. So you could maybe do that numerically. Turns out that there's actually a way of writing this that's kind of helpful, and it's called an external fractional function. External fractional function. So what external fractional function does for you is it takes this integral, it tabulates it out, and you just have to give it one argument, and then you get back the fraction of light that's in that band. So what I mean is, if we were to plot out our power like this, so you have down here wavelength, and here we have EB lambda, and I plot a curve, and it looks something like this. If I wanted to know the total light that was between, say, 0 and some lambda 1, I'm basically just asking for this integral here, right? This integral in this region. So you go to this external fractional function, you plug in your wavelengths, and you also need to somehow account for the temperature. So what the external fractional function does is it defines this, this function as follows. It says, over here, it says f 0 to lambda 1 is equal to EB 0 to lambda 1 divided by EB, right, the total emissive power. We then substitute in Planck's law into the top numerator part there, and we end up with the equation, let's just do this, f 0 to lambda 1 is equal to the integral from 0 to lambda 1. Sorry, what I'm going to do is, when we're making this evaluation, you end up with this variable. So you see here we've got lambda times t. You have lambda. We're doing this d lambda. We know that there's a relationship between lambda and temperature, or like the intensity and temperature. So actually what I'm going to do is I'm going to make this substitution where I say we're going to integrate this equation in terms of the product of lambda and temperature. Okay, so it becomes lambda 1 times temperature. And it slightly changes the equation, but it actually makes it so we can treat that product as a single variable. So that looks like this. It looks like the integral of, what's it, C1 divided by sigma lambda times t, that's our variable, to the 5th power, times the exponential of C2 over lambda times t minus 1. OK, so this fractional function, external fractional function, is defined this way. Somebody's gone through, taken the values of lambda and t, evaluated it, and gives you back a function that you can then just look up. So what you need to do, if you're going to use this function to get the fraction of light, right, fraction is, it's a number between 0 and 1, because we're always between 0 in the numerator and the total in the denominator. You just go plug in your lambda times t, and you get back whatever the function value is. So it turns out then, if you believe me, that you can take the product of lambda times t. You take that, so what this is saying is I have a temperature. I know the surface temperature, the body temperature. I take the temperature, I multiply it by a wavelength, and I let that wavelength vary. I can then take that product, plug it into this function that we just derived, And that will tell me the amount of power that exists between 0 and that wavelength. Okay? So again, product of temperature times wavelength gives me the fraction of power below that wavelength in the blackbody emissive spectrum. So this is programmed into like ease. You could look it up there. I think there's probably a function in the book as well. But this is the external fractional function. You can use this then to like evaluate. Let's say I want to know from 0 to this product here, and I get that. You could also do the same thing for looking at a specific range. So if I wanted to know between the range of 2,000 and 5,000 how much is emitted, or you could also do that. So that's actually the subject of the top hat question, which I will ask now. So the question is, which of the following is a valid use of the external fractional function to determine blackbody radiation in the band lambda 1 to lambda 2? So again, I said, let's pick a band and look at how much is just in that range. So is it the temperature, let's say this is a single temperature, times the fractional function, minus the temperature times the fractional function? Is it the fractional function of the product of lambda 2 temperature 2, lambda 1 temperature 1, or is it the difference of these two, where it's the product of two wavelengths at the same temperature? Okay, so most people think it is the last one here. A few people think this one. Nobody thinks this one, so this is wrong. I can just show you what the answer is. So you are almost all right. So this everybody agrees is wrong. This one is wrong. It's close to this, but what we're saying is it's wrong because if I'm looking at this external fractional function, it needs to be a body that's at a single temperature. It needs to be one temperature associated with this thing. Because if you start changing the temperatures in the two different cases, then you have like a different basis for the curve, or a different basis for the EB curve. So it has to always be the same temperature, the same basis temperature, but you're just looking at specific wavelengths at two different positions there. So you have now the understanding of the black body, the real surface. We'll talk more about real surfaces. And you can maybe evaluate the amount of light that's emitted in a wavelength. I think that's probably a good place to stop. What we'll do next time is we're going to talk about view factors. So view factors are how you determine how much light is going from one surface to another in space.